Hello, am I audible to you guys?
Yes, ma'am. Yes.
Okay. It's too much work for convocation. I have another meeting very soon. Anyways, I need to quickly start something. Okay, so in last class, means yesterday we mainly discussed about the time complexity and the space complexity. So space complexity means the memory requirement to execute a complete code. So for that, each of the variables, constants, and some extra words like sometimes return and all extra space are required. Okay, so each of these instructions takes 1 unit of time. Okay, starting from variables, constants, and all. Next is the time complexity. Time complexity is the most important part of any algorithm for analyzing any algorithms because we are mainly concerned about how much time your program can take to finish execution and complete a task. So mainly our running time depends uh, on input. Then other than that, I already mentioned some like environmental factors like uh, processor speed, whether it is single processor or multiple processor, then what is the read-write speed of your memory, then whether your machine is 32-bit or 62-bit. Normally 64-bit machines are a bit faster than your 32-bit. Okay, so running time depends on these four things: input, then other environmental like the configuration of your machine, memory, and processors. Okay, but here mainly we are concerned about the input size. Okay, so your input of the program will decide the rate of growth of the time. Okay, and time complexity we mainly calculate in terms of ratings: best case, worst case, and the average case. Best case means the minimum number of steps your program will take. Okay, if your program will take less number of steps and it will complete the task, will be the best case. Okay, then worst case is like the what will be the maximum time your program can take to finish a work. Oh, technical. Yeah, so an average case is just the average time. Okay, so for any programs, we always try to find out the three things: best case, average case, and the worst case. So for each of these types, we have certain things. Means we have certain terms for that, and it is known as asymptotic notations. Okay, so asymptotic notations are mainly for your complexity analysis of your algorithm. So we analyze the complexity of any algorithm, mainly for the time complexity. We use asymptotic notations. Okay. So time and space complexity, what is that? I have already explained. So let's see the space complexity first, how we can find out the space complexity. Okay. So for space complexity, I already mentioned in last class that is the total input space plus the auxiliary space. Auxiliary space means anything extra that you require to complete the execution. So here, for example, there is an algorithm, sum A and B. I guess I already showed you guys in last class also. And it's a start. Then this is the second line, C equal to A plus B plus 10 and stop. So total space will be 1 plus 3. Okay. Why 1 plus 3? Three variables A, B, C plus the constant term Y. Okay. So space mainly depend on the data types of your variables and constant time, and it will be multiplied accordingly. Okay, so this is just a normal way of finding out what will be the input. These are like 1 unit, 1 minute. But for every variable type, like we have different data types like int, boolean, floating point, and all. For each of this type, again, the memory requirement is different and it will be multiplied. So here is the table for that. These are the data types for Boolean, character, and all this. Normally, we are concerned about the main basic data types: Boolean, character, int, float, and short, and all. For Boolean character, unsigned character, requirement is 1 byte. For short and others, it's 2 byte. Mainly, we use int, float, long, and for that is the 4 byte. Okay. Then for the double and long, it is 8 bytes. So this is the table or the memory requirements you must know. This is even I covered in your PTS class in the last semester that each of these data type requires certain amount of memory space. Okay. So now what will be the space complexity for this one? Any guesses for this one? Instead, ABC returns it. For this particular piece of code, what will be the memory requirement? You can write it down and check this table. Any guesses? Just type your answers in the chat box or you can also unmute yourself. Example 1 and 3, return auxiliary and input space, boom, 2. Okay. Auxiliary space in this case, so 1. The extra 10 is there. Okay. PDS and say the answer is 4 for the other one. Any other guesses for this one? Check to table. For in float 4. So here you can consider them as 2. Just any more guesses? Okay, so here total memory requirement will be 20 bytes. How? A, B, C, and Z. There are four variables and all of them are integer types. So 4 into 4. Right? See, here there is a line with the depend on the data types of the given variable and constant type, and it will be multiplied accordingly. This is just unit of time. Okay, 1 3. Here I didn't mention whether it is integer or float and all. This is a simple example how you can calculate it. Okay, so here I just showed how auxiliary space and input space work. Input space, three variables, and one is for the extra constant, which is the extra part. But in this case, I have mentioned the data types of the variables too. Okay, so therefore, this ABC all are integer types, and additional 4 bytes is required for the return value. Remember, in most of the instructions take a certain space. When the return code will take certain amount of space. Now, why is it 4 byte? Because it is returning Z, which is another integer type. Right? Z is integer, so it is returning here. So extra 4 bytes will come from here. So total memory requirements will be 4 into 4 plus 4 equal to 20 bytes. What if there is return is 0? Here I'm not returning the 0, right? If return type is 0, then it will be a simple constant type, 1 unit. It will take 1 unit if I don't define whether it is integer type or not. Here it's returning Z, which is the integer type, that's why 4. If I just write return 0, then it will just take 1 unit of time. Sorry, this is not time, this is just space. Okay, so this is another example. So here I'm taking one function, sum, then one array, and variable. Okay, here n is the length of the array. We don't know the size of the array here. One piece of code is that int x equal to 0, then again one loop, one instructions, and the return. So what will be the memory requirement for this case? So there will be 4 into n bytes of space required for the array, because array is your integer type, right? So 4 will come for the integer data type. Now we don't know the length of the array, so we just consider it n. Okay, if you know the size of the array, for example, if your array size is 10, then the memory requirement for this array will be 4 into 10 equal to 40. Okay, n will be the length or the size of your array. Then 4 bytes each for x, n, and I, and the return value. What are the other integers? One is x, and I have n, then there is I. Then there's again return. So each of them will take extra 4 bytes. So total memory requirement will be 4n plus 16. Okay. Now if you know the value of n, like the size, like if it is 10, it will be 40, 40 plus 60. Okay, just see this code and read this part again. How many variables? X, I, n. Okay, 3 variables. Then there is again a return type, which is also an integer type. So total 4, and each of them will take 4 bytes because all of them are integer types. So that 4 into 4, or 4 plus 4 plus 4 is 16, will come here. And this 4 n part is for the array part. Integer array, that's why 4. Then n is basically the size of the array or the length of the array. Is this part clear?
Ma'am, not properly. Can you repeat why it's 4n?
4n. Okay. Here, your array size is int a. Okay, so 4 byte is for your integer data type. This will take 4 bytes. Correct? Now here I don't know the size of your array. Okay, if now I write it's 10, then the memory unit will be 10 here. 4 into 10. See, n is the length of the array. So that means what? Here I have considered the size of the array is just n. Therefore, it's 4n. If your size is 5, then it will be 4 into 5. If size is 3, 4 into 3. If size is 4, 4 into 4. If size is 10, 4 into 10, like that. N is just the length of the array.
Okay, understood, ma'am.
Okay. So in an array, it's not a single variable, right? Like x, I, n, these are single variable. They will just take one unit of time, that means 4 bytes. Correct? In an array, you can keep more than one variable. You can keep 1, you can 2, 3, 4, and multiple. So depending on the number of items in your array, it will take the space. Since it is integer, it will be multiplied. Okay, if I simply write a equal to 10, the memory requirement for this array will be just 10. Okay. Now if I mention it int a10, that means what? I have to multiply the integer part 2. Okay, so n is just the size of the array. Means the amount of items or records stored in the array. So total memory requirement is 4n plus 16. 16 one I guess already clear. X, I, and n three variables. Then there is a return type, which will be also gain an integer type. So 4. So if your array size is 10, for example, then it will be 4 into 10 plus 16. 40 plus 16. So 56. Clear now? Okay. Now, in as I mentioned earlier, like auxiliary space, which is just extra space or temporary space. In swapping, we use a temporary variable, right? So even that temporary variable will take some amount of time. So auxiliary space is anything extra. So space complexity is mainly we consider total space taken by the algorithm with respect to the input size. Hmm? Okay, so now the thing is, this is just the representation. Okay, when we write the total amount of space is like 56, total amount of space is 20 bytes and so on. But when we write it conventionally, we don't write it like this. We again use some kind of notations. If I write what will be the space complexity for example, you're sorting an array or something. So I'll just say space complexity is ON. N means it's the constant time. Okay, or constant speed. Sometimes I'll come to that part, what is O and all. Just that we don't represent the exact value sometimes. In terms of representing, we just write a constant space. If it is a constant time term, then we just write ON. So this piece of code is going to take ON space. Okay. And sometimes we also say it needs only one space. Okay. The moment we will start all these data structure things like stack, queue and all this data structure, we will see the programs, right? Then you will learn more. Means how we can calculate the space complexity of an algorithm. Okay. So it will be more clear then. Just now you just know the concept how we can calculate the space. Remember, for each variable, for each constant, the return types, and you have to also check the data types. Okay, so main part is the asymptotic notations. This is mainly for the time complexity. As I mentioned earlier, we are mainly concerned about time complexity more than the space complexity. Okay. So what are the asymptotic notations? So the study of change in performance of the algorithm where the change in the order of the size is defined as asymptotic analysis. Okay. So there are certain notations. With the help of these mathematical notations, we find out the running time of an algorithm. Okay, that means what? If you write an algorithm, it should have a particular time, right? It should be finished in a particular amount of time. Your program should not be in like run for infinite time. If it does, means it's just stuck in infinite loops. We don't want that. Remember, the first rule of algorithm is that it should be finished, it should be definite, it should be finished in a particular amount of time. So what asymptotic notation does, it just set the upper limit and the lower limit for the algorithm. Means whenever you run a program, it checks the upper bound and the lower bound for the program. Okay. So there are three types. Okay. Mainly we use asymptotic notations to compare one algorithm to other. Okay, we directly cannot compare two algorithms side by side because it also involves like hardware of your computer. Means suppose, as I mentioned earlier, for one program or one problem, you can write different algorithms, right? For a simple addition of um, numbers also, you can write your algorithm in a two different way. Like everyone has their own way of writing the program. So algorithm will be different too. So now we cannot directly compare the algorithms. Means which algorithm is better one. Why? Because there are other things involved, like the hardware you use. My computer is different than yours computer. So maybe your computer is faster than mine, and so on. Okay. Then your CPU model, processor generation, OS, everything is involved. So therefore, we simply calculate the time and space for both algorithms. And for that, we use this asymptotic analysis. Okay, so asymptotic analysis we mainly use for time, but it is also used for your space also. Okay, and for both, input size is very important. We just consider everything in terms of input size only. Okay, so there are basically three notations: theta notation, omega notation, and big O notation. Theta, omega, and big O notations. Okay. And in asymptotic notations means when we calculate the time, we always ignore the constant factors and small input size. We are only concerned about the main input values. So what are these notations? Okay, each of these three notations are used for different time complexity. Okay, then apart from these three, we have big O, big omega, small theta, small omega, and small O notation also. And here these are all big theta, big omega, big O. So here comes the big O notation. Okay. Big O notation, always remember, it provides the upper bound of the running time, and it is always provides you the worst case complexity. Okay, so whenever I ask you or anyone asks you the time complexity of an algorithm, mostly we mean the worst case. If in the worst case you are going to take lots of amounts of time, then it is not a good algorithm. And to represent the worst case, we always use big O. Okay, so for the big O notation, it always provides the upper bound. Remember that. Means your function should not cross that upper bound. And this is the main formula for your big O notation. Okay, OGN Fn, there exists a positive constant C and N naught such that big O is less than your function and less than a constant term CGN for all n greater than N naught. So here the curve for your main function. Suppose this is the curve for your program. Okay, and this is the upper boundary. So this is the upper boundary and your program should be limited to this amount of time only. It should not cross this limit. Okay, therefore your function should be in between 0 and CGA. Okay, so this is the constant term and not. So your n total amount of input size should be always greater than n naught. Means it's a random time, a random input value. Okay. So this is the most commonly used notations and defines the upper bound. That means maximum time taken by the algorithm. Okay. So for big O, we can have different amount of time. Sometimes you will see some algorithms take O(n) time, some algorithms take O(n) square, some algorithms take O log n time, and so on. Okay, so each of these have some priorities. Some are good. If O(n) is still good, if it's taking O(n) square, this is slower. Okay, this is not good. O(n) time is better. It is better. Better than it takes less time. That means it is better. O(n) time is better than O(n) square time. So if you are writing two programs for the same solution and one algorithm is taking O(n) square time and one algorithm is taking O(n) time, that means this one is the better than this one. It takes less amount of time. O(n) square means it is exponential. So there are again certain formulas like O log n time is better than, means takes less time, means better than O1. Some algorithms take just single amount of time, O1. Okay. Again from better, it is On. Okay. Then On log n is better than On. Then comes your On square. Then comes your O to power n. Then comes your O factorial n. These are the all possible time complexity, worst complexity for an algorithm. Okay, you will see how we can calculate these things. Okay, just we are going step by step. First, we will just know what are the notations for each time complexity. So just remember, big O notation is used for the worst case complexity, and it provides the upper bound. Okay. Next comes the big omega notation. So omega provides the lower bound. Okay, omega provides the lower bound, and it is used for the base case complexity. That means the minimum amount of time your program can take. Okay, so here you see it provides the lower bound, and your function for the algorithm lies above your main limit. This is the limit, it will stay above. It provides the lower bound. Okay, so here is the formula for your omega notation. So it will simply give you the minimum amount of time taken by the algorithm, or the lower bound. Also, you can say the best case. Okay, the third one is the theta notation or big theta notation. So what big theta notation does, it provides a lower, that means it gives you the mid ground. It represents both upper and lower bounds, and it is mainly used for the average case. Okay, so here is the example or the formula for your big theta notation. So here you can see this is the function for your algorithm, and theta notation provides both lower bound and the upper bound. So your function should lie in between these two limits. So therefore it is the average case. What will be the average time to finish the program or your algorithm? Okay, just remember these three things. We'll discuss about it more in next class. If you are still confused, it might be a bit difficult for you guys. I know this is like a first thing you are getting in terms of algorithm, and it's lots of mathematics involved. Just remember three terms: big O for upper bound. It will give you the worst case. Then comes your omega, which will give you the lower bound or the best case. And then comes the theta, some results, which will give you the average case complexity. And you just have to remember this formula. It's not that difficult since it gives you the upper bound. That means function should lie in between 0 and the limit CGN. Okay, C is just a constant term. Then for the best, since it provides you the lower bound, that means the function will stay above your limit. That means CG should be in between the main function and the zero. That average case, the function should lie, it provides both upper and lower bound. So for both, the function should lie in between C1GN and C2GN, other two functions. Okay. So I guess this part I'll continue in next class, how we can calculate the time complexity. Okay. So this meeting is going to end. So just remember these two parts. Are you guys able to follow it? At least what is the space complexity, what is time complexity, what are the notations. I'll tell you how you can find the time complexity later on. Because for every algorithm or every program we are going to do, we'll find time and space complexity. Mainly we are concerned about the time complexity. Okay. Yeah, notations are not easy. This time you are just getting 3 notations. Then in next semester you will get total 6 notations. There are 6. These are all big. Just remember the other 3 are the small. Here you are getting big O, big theta, big omega. Next semester you will get small o, small omega, small notations. Okay. So here it's like they are giving some limit, means giving hard bound. Then the smaller one is like giving a bit relaxations like that. Notation, just remember the time complexity particles. The 3. Big O worst case, upper bound. Then the omega is for best case, lower bound, and theta is your average. Okay. But most of the time we are only concerned about the worst case. Even if we, in some places you will see, even if they find out the average case or best case, till they write in terms of big O only. Okay. Okay. Okay, that's all for today. I don't have anything to catch. Thank you all. We will continue in next class. Okay? Next class we will see how we can calculate the time complexity.
Excuse me, ma'am.